Hello student to the course of Physics of Linear and Nonlinear Optical Waveguides. So, today we have lecture number 36 and in today's lecture we will try to understand the very important theory called couple mode theory, which is related to coupler. So, in the last class we already started the concept of directional coupler, where we mentioned that if I have a structure like that having 4 ports, then if I launch a light here in this port, there is a possibility that I can have the light here, which is called switching. So, that means there is a transfer of energy from one waveguide to another waveguide, which is placed very close to each other. So, let me draw a rough schematic diagram. Suppose these two waveguides are placed very close to each other and I have a wave here, initial wave, and at certain distance what happened, this wave will come here at this waveguide. So, this is waveguide 1 and this is waveguide 2. So, I launch the light here initially, say at z equal to 0 point and some z equal to say some length L c. I can find that this is a critical or coupling length, and what happened, that entire energy can transfer to these new waveguides. Along this direction we have the propagation. So, this is my z direction. So, I can now write this waveguide in this draw the refractive index profile of these two waveguide in this way. Two waveguides placed side by side. So, this is the structure of the waveguide. This is waveguide 1 and this is waveguide 2, and they are placed very close to each other, and z is perpendicular to the plane. So, along this direction we have z, and along this direction suppose we have x. So, refractive index is varying along this direction. Two waveguides, they are placed side by side. So, what happened that we can have some general modes of these waveguides. These waveguide can be considered to a single waveguide, and if I consider this a single waveguide, I can have a general mode, say in this form. This is called asymmetric mode. Also for this waveguide, I can have a mode like this. Which we call the antisymmetric mode. Now, using the first principle, we will try to understand the propagation of these kind of modes in the waveguide and how this energy transfer is possible in the waveguide. So, let us start with the very first thing, and this is a very important theory. We call this a coupled mode theory. Using the coupled mode theory, we try to understand how this mode will going to evolve inside the waveguide. Not only that, how the power will going to transfer from one mode to another mode, and all the necessary information are going to extract. So, in this particular course, we will calculate this coupled mode theory rigorously. All the rigorous mathematics will be done here. So, it will be a little bit lengthy. So, let us start with the first equation that we have and always we use, and that is the wave equation, because when we deal with the wave, then we need to write this wave equation at first. So, that we know. This is the Maxwell's wave equation I am writing, where psi is a general mode in this waveguide. Now, I can define psi, big psi, which we call the general mode. So, big psi can be defined as say psi 1 plus say psi 2, where my psi 1 is defined in this way. I have an amplitude which is varying with respect to z, that is the important term I am putting here. Then I have psi 1 x y, this is a x y dependent term, and then the propagation term e to the power I beta 1 z minus omega t. Okay. Then psi 2 I can also define bz x y e to the power I beta 2 z minus omega t. So, this way I define psi 1 and psi 2, assuming these modes are for these fields are for these two waveguides like this. So, this is one waveguide and this is suppose another waveguide I draw in this color only, and the fields are defined here in such a way that this is for psi 1 and this is for psi 2. So, that the total mode is big psi, which is the addition of these two. So, superposition of psi 1 and psi 2 will give us the total mode of this system, whatever the system is drawn here. So, that means my psi is A z. So, amplitude, the important thing is the amplitude. This amplitude now become a function of z, because when the mode is propagating these two. So, what happened that there is exchange of energy from this mode to this mode. So, that is why the amplitude will going to change over the z distance. So, that is why A and B should be a function of z. Then psi 1 e to the power of I beta 1 z plus B z psi 2 e to the power of I beta 2 z, and then e to the power of minus I omega t. That is my total field by definition. Now, this total field will going to satisfy this equation, this wave equation, Maxwell's wave equation. So, now if I put this into this Maxwell's equation, I can have few terms. So, the first thing I can do, I can extract this term quite easily, because the t dependence is only sitting here into the last term e to the power I omega t, and if I make a double derivative with respect to time, then it should be minus of omega square and then big psi. That is my left right hand side term, whatever is here. Now, also I can write del square psi is equal to minus of omega square c square n square big psi, which is minus of k 0 square n square big psi, because omega by c is nothing but the propagation constant of the free space, which is k 0. So, that we find. Well, these can be written as, this is the notation we have been using for a long time, that I divide this del square operator into two parts. One is the transverse component and another is the longitudinal one, that is propagating, that is along the propagation distance z, then plus k 0 square n square big psi is equal to 0. Note it, this transverse component of this quantity is this one, just this derivative. Well, now I put this psi, whatever the psi I defined in the last page, this one, I am going to put it here in this equation, and if I do, I can have simply, so a e to the power of I beta z, then the derivative with respect to x and y. So, I can write simply this one, this is for psi 1, and for psi 2 I have b e to the power I, okay, here we have beta 1. So, beta 2 z, then the transverse part, this one, plus now I have to execute this z derivative, and if you look carefully, we have two z components here, one is sitting here a z and another is here a function of z and b function of z, and another is e to the power I beta 1 z. So, we have to be careful enough to execute this z derivative, which is a double derivative, and if you do carefully, then I can have a term like this. Plus 2 I beta derivative of x minus beta 1 square a e to the power of I beta 1 z, that is one term, plus another term is similarly, exactly similar way, I have this, it should be 1, this should be 2, it should be b. Then minus of beta 2 square b e to the power of I e to the power I beta 2 z. This thing will be equal to 0. So, I put all the terms here, and then after putting all this term, so let me use, so this is say equation 1. So, equation 1, and say this is equation 2, and this is from equation 1 and 2. We have this one. So, I just put this value of psi in equation 1 and I am getting this one. So, these things I can simplify a bit, and if I simplify, okay, let me write it again, that this thing is a e to the power of I beta 1 z, then I have few terms like this, psi 1 plus k 0 square n square minus beta 1 square psi 1, this is one term. Another term, the similar way, I have b e to the power of I beta 2 z, and then plus k 0 square n square minus beta 2 square psi 2, this one, and plus 2 I beta 1 del z a psi 1 e to the power of I beta 1 z plus beta 2 del z beta, then psi 2, then e to the power of I beta 2 z, bracket close, is equal to 0. So, I am making one approximation. So, let me first write down this approximation, that we neglecting these second order derivative terms. So, this is a slowly varying approximation. So, let us quickly understand what we have done here in this step. So, this is step 1 and this is step 2. So, from here I have step 2. So, in step 2 what happened, that I just take this beta 1 a term to here and beta 2 square, beta 1 square a term and beta 2 square a term to in this equation, this part and this part. So, that I can have a term like this one and this one, and rest of the things are straightforward. I have 2 I beta 2 first order derivative with respect to z b and 2 I beta 1 first order derivative with respect to z of a. These two terms I just put together and this is the term, and I neglect this term and this term, because compared to the first order derivative these two terms are small. So, we simply neglect this term and we call it a slowly varying approximation. Now, let us go back to, now there is a reason why we put this term here, this term and this term, we write it for a reason, and let me draw once again the structure. So, our structure was like this, two waveguide placed side by side. This is refractive index say n1, this is refractive index say n2, two different refractive index. Then I can have a equation that should satisfy in general for these two waveguides is this one. when j is 1 and 2. So, for psi 1 and psi 2 we can have these solutions of these waveguides. If this waveguides n2 is not there, for n1 waveguide I can have this equation, and if n1 is not there I can have, if I have only n2, then I can have the solution, Maxwell's equations or the mode equation for psi 2. So, for psi 1 and psi 2 specially I have an additional equation in my hand, and this additional equation reads like this. Now, I am going to use this equation here because I already have this almost the identical form here. Only thing you should note that this n here is the refractive index of the entire system, whereas this n1 and n2 are the refractive index of the individual waveguides. If I just now remove this waveguide n2, I have only one waveguide, and then this equation going to satisfy by psi 1. If I do not have n1, only have n2, then again psi 2 will going to satisfy this equation. So, psi 1 and psi 2 individually will going to satisfy this general equation. I just write this general equation by putting a suffix j, so that I can understand that this equation will be satisfied by 1 and 2 or psi 1 and psi 2. So, I am going to make use of this information here and try to understand that what happened after that. So, let me erase these lines because this is just to highlight that. So, I am going to use this here. Okay. So, now if I use this equation there, then I can eventually have some equation like this. Beta z then psi 1 k 0 square, n square already there. So, I incorporate another n1 square here plus beta, it should be 1 e to the power of I beta to z, and then psi 2 k 0 square n square minus n2 square. These two term additional term I have, because here if you look carefully, so this term that I have n. So, this minus beta 1 square psi 1 square psi 1 I just replace here. So, these things is nothing but the transverse components. So, when I have a transverse component, then so let me do one thing because I need to write this. So, I am going to use this equation. So, transverse component psi j plus k 0 square n j square minus beta j square psi j equal to 0, j is 1 and 2. I am going to use this equation here, and eventually I have this equation, this plus the rest term is as usual 2 I beta 1, then the first derivative with respect to z a psi 1 e to the power of I beta 1 z plus beta 2 first derivative with respect to z of b psi 2 e to the power of I beta 2 z, this is equal to 0. This n1 square, this is the difference between the refractive index. So, I can write this difference as say delta n1 square and n square minus n2 square as delta n2 square. So, I just write these two difference between these two refractive indexes. Mind it, n is the refractive index of the entire system, if I consider these two as a single system, and N1 and N2 as the individual refractive index of these individual waveguides. So, N1 is a refractive index when these waveguides is not here, and N2 is a refractive index when N1 is not there, this waveguide is not there. But if I put these two waveguides together, then there is a general refractive index, there is overall refractive index of the system, and that refractive index I defined as a N, and psi 1 and psi 2 as the solutions are the field solution of individual waveguide. Well, after that, here I have one term called beta, and so let me write the next thing, that A. So, from this equation I can write as A, I divide the entire equation with e to the power, say e to the power of I beta z. If I divide the entire equation to e to the power I beta z, then I can have A k 0 square. So, let me see what was there, A k 0 square, then delta n 1 square psi 1 plus B e to the power of I delta beta z, because I divide. So, that is why I should have some kind of delta beta. So, what delta beta I will show soon, N2 psi 2 plus 2 I beta 1 del z A psi 1 plus beta 2 del z beta psi 2 e to the power, again whenever I have B, I have this term. This is equal to 0. Note it, delta beta is equal to beta 2 minus beta 1. So, what I essentially do, that this equation I have, I put n1 n square minus n1 square to delta n1 square, and then I divide the entire equation to e to the power I beta 1 z. If I divide, then this term will not be here, this term will be e to the power I beta 2 minus of I e to the power of minus of I beta 1 z. So, that I write in this way, delta beta z, where delta beta is beta 2 minus beta 1, which is the difference between the propagation constant of the two modes that is propagating here. So, it is, this is the waveguide I have. So, this is the propagation constant here, and this is the propagation constant here in absence of these two. So, delta beta is the difference between these two propagation constant of these two individual modes. So, today I do not have much time to proceed more. So, I should start in the next class, I should start with this equation and then try to complete the calculation. As I mentioned in the starting of the class, this should be a lengthy calculation, but it is important to understand how for a couple mode theory, how we can extract the information of the amplitude and how the amplitude is changing with respect to z. So, with that note, I would like to conclude the class. So, see you in the next class with the additional calculation or the further calculation with this couple mode theory. So, see you and thank you.